Welcome back to AI Paper Podcasts. I'm particularly excited about today's deep dive. We're going to crack open a paper that honestly aims to make AI development a lot more efficient, maybe a bit less guessworky. We're talking about AI model distillation, specifically how to optimize it using these things called distillation scaling laws. Our source today is the paper aptly titled Distillation Scaling Laws. It's from a really strong team. Busbridge, Shadani, Weers, Ramapuram, Litwin, and Webb, representing both Apple and the University of Oxford. So, okay, what's the big picture here? What are we trying to get you out of this? Well, imagine you could cut out a lot of the trial and error when creating smaller but still powerful AI models. This paper introduces a novel scaling law. It lets you estimate pretty precisely how a distilled AI model that's a smaller student model will perform. And it bases this on how much compute you invest and, crucially, how you split that compute between training the student and potentially training or using the teacher model it learns from. The core finding, really, is that this law can dramatically reduce the risk and the guesswork in large-scale distillation. It shows you the most compute-efficient paths. It even gives practical sort of recipes for different situations, like whether you already have a teacher model ready to go or if you need to build one from the ground up. And importantly, it sheds light on when distillation actually beats standard supervised learning finding. It often does, but only up to a certain point, a compute threshold. But here's a key takeaway, maybe even the kicker. If you're just distilling one student and you also have to train the teacher from scratch just for that student, well, surprisingly, just doing traditional supervised learning might be the better bet, efficiency-wise. So this work really pushes our understanding forward. It helps us design experiments better, potentially saving a ton of resources.
All right, let's unpack this a bit more then. The world of large language models, these, incredible AI brains powering so much, now they have this major challenge. They are just huge, massive. And while they're incredibly powerful, these big compute optimal models, they come with a pretty steep price tag.
We're talking high cost just to run them, the inference costs. Plus, big carbon footprints, and frankly, they can be quite slow for many real-world uses.
Yeah, and what's really striking is that the cost to run the model, the inference cost over its entire life cycle, that can often dwarf the initial cost to train it in the first place. That's not a small detail. It's a major roadblock for getting these things widely deployed and accessible. It stops a lot of cool ideas in their tracks.
Right. And the industry's go-to response often seems to be, well, let's just overtrain smaller models. Basically just throw massive amounts of data, like trillions of tokens, at these smaller architectures to try and force them to reach similar capabilities. But, you can guess, that's also incredibly expensive and takes a long time. It feels a bit like brute force.
Exactly. It begs the question, doesn't it? Can we get that same high performance from a small, efficient model, but without that astronomical training cost? And that's really where distillation comes into the picture. It offers this potential shortcut, a smarter way, perhaps.
Okay, you mentioned distillation. For listeners maybe less familiar with the specific technique, can you unpack that master artisan teaching and apprentice idea a bit more? How does that actually work with AI models? What's the real advantage over just, training a small model on raw data?
It's a great analogy, actually. Distillation, and this goes back to Hinton and colleagues, is essentially this technique where you have a big, capable model, the teacher, which has already learned a lot. And instead of the small student model learning directly from raw, often messy data, it learns from the teacher's outputs. The teacher provides, let's say, softer, more nuanced targets. Not just this is right, this is wrong, but more like probabilities or intermediate representations, the wisdom of the teacher. The advantage is the student gets this pre-digested knowledge. It doesn't have to figure everything out from scratch, which is computationally very expensive. It kind of inherits the teacher's refined understanding.
So it's learning the patterns the teacher found, not just the final answers. And there are different ideas about why this is so effective, aren't there?
Oh, absolutely. There's several theories. One popular one is dark knowledge transfer. The idea there is the teacher isn't just telling the student the right answer, but it's also passing on information about why other answers are wrong or how wrong they are, through the probabilities it assigns even to incorrect outputs. This dark knowledge, gives the student a richer picture of the problem space. Other ideas suggest it acts like a form of regularization, smoothing out the learning process or maybe reducing noise from the raw data. But whatever the exact mechanism, distillation pre-training has been really key for some very powerful models we see today. Gemma, Gemini, Minitron, AFM, they all use it. Although it's not foolproof, some studies, like one by Liu and others in 2024, have found cases where it actually produced worse models.
Which really underscores why understanding how to do it right is so important. You can't just throw any teacher at any student and expect magic. And that's exactly what this paper digs into, bringing some solid science to allocating resources for distillation.
Precisely. And they were incredibly thorough. They trained transformer models, both students and teachers, across a huge range of sizes. Think from about 143 million parameters, which is decent, all the way up to 12.6 billion. That's a massive scale. And they use data sets from a few billion tokens up to over 500 billion tokens. This sheer breadth of experimentation across scales and data sizes is what allowed them to develop their main contribution, this distillation scaling law.
Okay, so a scaling law. At its core, that just predicts how a model's performance, usually measured by something like loss, changes as you give it more resources, bigger size, more data. For standard supervised learning, we kind of know the drill. Cross-entropy loss tends to follow a predictable power law. Lower loss is better, and it improves smoothly as you scale things up.
Right. And this new distillation scaling law, it's their equation 8 in the paper, predicts the student's loss, which they call LS. It depends on 3 things: the student's size, NS, the amount of data it's distilled on, RDS, and this is the crucial part, the teacher's loss, LT. So it's the teacher's actual performance, how good it is, that directly impacts the student, not just how big the teacher is or how much data it saw originally.
Interesting. So all that matters about the teacher from the student's perspective is encapsulated in its final performance score, its loss. That simplifies things quite a bit. But you mentioned it's not a simple linear relationship.
Exactly. That's where it gets really fascinating. The way the teacher's performance, LT, affects the student's performance, LS, isn't straightforward. It follows what they call a broken power law. So the relationship behaves one way up to a point, and then the behavior fundamentally changes. It's not just a smooth curve downward. Think of it like maybe you're learning something, and at first more complex instruction helps, but then it hits a point where it's just too much, and your learning rate suddenly changes or even reverses.
And that leads directly to this idea they call the capacity gap, right? Is it like if you have, I don't know, a world-class physicist trying to teach basic addition to first graders, they might actually make it harder because their explanations are too complex? Is that the kind of idea?
That's a perfect analogy. Yes, the capacity gap is exactly that phenomenon. A teacher that is too capable, too far ahead of the student, can actually lead to a worse student performance. The paper is careful to point out it's not just about the difference in model size per se, although that plays a role. It's about a mismatch in their fundamental learning abilities. Like the student's ability to represent complex concepts, its hypothesis space, and how well it can actually learn from the teacher's guidance, its optimization capabilities. If the teacher's output is just too complex for the student's capacity to model effectively, the student struggles and his performance suffers. They even show this empirically with some other experiments, like using kernel regression and synthetic data, demonstrating this kind of U-shaped curve. Student error goes down as the teacher gets better, up to a point, then it starts going up again.
Wow, okay. So a teacher can genuinely be too good. That's pretty counterintuitive. Understanding that dynamic is cool, but how does this translate into practical advice? Like if I'm an ML engineer, how do I use this? That seems to be where the paper really provides value. They lay out these 4 practical scenarios for allocating compute, right?
Exactly. This is the really actionable part. They consider the compute cost, which for distillation isn't just training the student. You also have to think about the teacher. Are you paying compute costs just to generate outputs, the logits inference during the student's training? Or in some cases, do you even have to factor in the cost of training that teacher in the first place? Logits, by the way, are just the raw scores, the model outputs before they become probabilities. They carry more info for the student. And it's all measured in FLOPs, floating point operations, basically compute power. It's about optimizing those FLOPs.
Okay, scenario 1, the best case. Teacher's cost is fully amortized. Basically, you get the teacher for free. Maybe it already exists and is running anyway.
Right. In this sort of ideal world, if you have a relatively modest amount of data or compute budget for your student, distillation looks really, really good, highly efficient. But and this is a key clarification they make, if you have enough compute or tokens to really push the student model hard, eventually good old supervised learning, training directly on data, will catch up and either match or even outperform distillation. So distillation is great, especially on a budget here, but it's not necessarily the ultimate solution if student resources are unlimited.
Okay, that makes sense. What about scenario 2? You have a teacher model already, but you do have to pay for its compute cost during the student's training, the teacher inference cost. This feels pretty common.
Yeah, very practical. In this case, they find the optimal teacher performance. The target loss for your teacher should actually decrease as a power law relative to the student size. This kind of confirms older observations that bigger students often benefit from bigger teachers, but frames it in terms of performance loss rather than just size. And the interesting tactical implication here is that it's often optimal to overtrain that existing teacher. Push it to get the absolute best performance possible, even if that means using some compute budget that could have gone to the student's training directly, because the quality of the teacher's guidance is paramount in this setup.
Huh. So invest more in the teacher's quality, even if it slightly shortchanges the student's raw training time. Okay. Then scenario 3. You have to train the teacher from scratch, but you plan to reuse it for lots of different students later. So you amortize the teacher training cost, but maybe not the inference cost per student. The teacher pre-training scenario.
Right. Here, the optimal strategy shifts. The best teacher to build for this purpose turns out to be a supervised, compute-optimal teacher. Meaning, unlike the last case, you wouldn't necessarily overtrain it. You train it efficiently, balancing its performance with its training cost, because that training cost is part of your budget now, needing optimization across all the students it will eventually serve. You want an efficient foundation.
Got it. And finally, the teacher pre-training plus inference scenario. This is the whole shebang, right? Train one teacher specifically for one student, paying all the costs training and inference, the most expensive route for a single student.
Exactly, the full cost scenario. Here, the best approach depends on your total budget. For smaller compute budgets, you'd stick with compute optimal teachers, like in the previous case. Train them efficiently. But as your overall compute budget gets larger, the optimal strategy actually flips back towards using overtrained teachers. This happens because, with a large budget, the cost of generating the teacher's outputs, logits for the student, becomes a more dominant factor compared to the initial teacher pre-training cost. So making those logits as good as possible, even via overtraining, becomes worthwhile again. It's a fascinating trade-off.
This really maps out the decision tree. So, boiling it all down, when should someone actually choose distillation over standard supervised learning? It sounds like it's not always the winner.
That's the crucial question, and the paper gives clear conditions. Distillation is generally more compute efficient only under certain circumstances. First, if your total compute or data budget for the student doesn't go beyond a specific threshold. And that threshold itself depends on the student's size. There's a point of diminishing returns for distillation. Second, and this is really critical, distillation makes the most sense if you either already have a suitable teacher model available, or if the teacher you're training will be reused for multiple purposes, maybe distilling many different students, or serving as a general purpose model itself. If your single goal is just to get the best possible model of a specific target size, starting completely from scratch with no existing teacher, supervised learning is often going to be your more efficient path, surprisingly.
So it paints a much more nuanced picture than maybe some of the hype around distillation suggests. It's a powerful tool, absolutely, but not a magic wand. Understanding these scaling laws seems essential for making smart strategic choices in how we develop these models.
I agree. This work really does provide a valuable roadmap. Knowing these compute optimal recipes for distillation, that means we can potentially create more powerful, yet smaller and cheaper to run models. That helps lower inference costs, potentially reduces the carbon footprint associated with massive models, and could even help democratize access to capable AI by making deployment easier. It helps minimize that expensive, time-consuming trial and error approach.
But this efficiency, this power to create smaller, capable models more easily, it comes with responsibilities too, doesn't it?
Absolutely. We have to consider the flip side. While the paper focuses on the how, we need to think about the what. For instance, it's known that distilled models can inherit biases present in their teacher model, sometimes even amplifying them, even if the student itself is trained on cleaner data. That's a risk. And, making it easier and cheaper to create highly capable, smaller models, while mostly a good thing for access and innovation, also potentially lowers the barrier for malicious actors. Creating targeted misinformation or other harmful outputs could become feasible with fewer resources. That's something the field needs to grapple with.
So what does this all mean for you, the listener, working in this field or interested in it? It suggests the cutting edge isn't just about scaling up bigger and bigger, it's increasingly about building smarter, more efficiently. The challenge then is taking these insights, these scaling laws, and applying them responsibly in your own work. It leaves us with a question to ponder. As we get better and better at creating powerful AI efficiently, how do we ensure this democratization leads to positive outcomes and guards against misuse? How can you use these laws to build not just efficiently, but also responsibly?